That being said, let's get started with our first talk, which will be delivered by one of the organizers, Michael Schaub from Acton University. And it is entitled Learning from Graphs and Data Networks, Overview and Outlook. So Michael, the floor is yours.
Well, thanks, Santiago, for the introduction and setting this up. So welcome also from my end. So this is going to be a brief intro talk about the kind of scope of topics we had envisioned for this workshop. And towards the end, I'll also touch upon a bit of research we have been doing along those lines. So, right, let's get us started. After looking at this beautiful airport network, the question is, why networks? And of course, for most people who attend this symposium, this is fairly clear. Networks have become really ubiquitous across the sciences and engineering. So whether it's biological systems or technical systems or social systems, right? You'll find those networks everywhere. And even though you find those networks everywhere, it's kind of interesting to see that there can be quite different perspectives and questions underpinning this network modeling. And basically, that has to do with what we actually want to model with such a network. And I just want to outline 3 different perspectives, even though we'll mostly focus on 2 in this workshop. And so the first one is basically networks as relational data. So the idea here is that what we measure is connections, right? So you go into a neuroscience lab, for example, and people there try to map out the connections in the brain. So the data, if you want, is now edges. So you can think about this as like relations that are measured. And what's our task? Well, our task is to model this data, typically using some sort of probability distribution. So we want to identify, let's say, certain patterns, and we want to know, are these commensurate with some structured probability distribution that we have on that data, right? And you know, you find this kind of flavor, let's say, of network science, which comes with tools typically from statistical inference, machine learning, and sort of computer science. When you look at things like connectomics, protein-protein interaction networks, protein structure, and what have you, right? And so the goal always is comprehend this graph-valued data and quantify the uncertainty. But then, you know, you have other people who look at networks quite differently. They're not interested in edge data, but they're interested in data that lives on the nodes. So you go into another neuroscience lab, for example, and here people record neurons. They record data that, if you want, is associated with a node. So if you abstract a neuron in a network with a node and the connections, the axons and dendrites and what have you between those by edges, then you get a distributed dynamical system, essentially. And now you're in the realm of dynamical systems, control theory, and in some sense, you could also think about this as like a graph signal processing type of framework where, you know, data sits on top of the nodes, and we want to understand how this data gets shaped, or how we can understand this data better by incorporating the structure of the network, right? So the question here is basically, how does the structure shape the data that sits on top of the network, and vice versa, right? So can we use, for example, data from the nodes to infer something about the network? And again, there are lots and lots of applications of this. And basically, these 2 perspectives are what we're going to cover in this workshop. But here's a third one that I thought I'd just briefly mention, is that if you do topological data analysis, for example, or these kind of things, then what you often start with is actually some sort of space in which you have data, and you construct a graph based on that data. For example, you can construct k-nearest neighbors graphs and so on. And now what you want to understand is the shape of the data using graphs, or maybe simplicial complexes, right? And so as you can see, there's like a range of different perspectives on this. And let's see what we can say about the first two in this workshop. And basically, the interesting thing here is, of course, that these things are not unrelated, right? I mean, we have dynamical systems that sit on top of networks, which are themselves, you know, uncertain and potentially dynamics happening on the edges as well, right? So the challenge, if we want to combine these two perspectives, really is what's the interplay between the node and this edge data? And, you know, having sort of set the scene here, I'm gonna go into a small example, which is some work we did actually together with Santiago and John Tsitsiklis at MIT, which is about network inference, which is really, you know, use node data to say something about the relations between the nodes. And here's a typical example of such an inference problem. So we're given the description of a coupled dynamical system. So the X would be a state variable that's associated to each node I, and we have ODE system, for example, where there's some local dynamics, right? So you can think of this sort of like as a self-coupling if you want. We have some external inputs to the nodes, that could be noise. And we have the interesting part, which is really the coupling that's mediated through the network. So in particular, we're thinking here about a pairwise coupling where, you know, we just have a linear sum over all the neighbors with a potentially nonlinear coupling G. And Aij here is, of course, I should say, right, the adjacency matrix of the network, which is 1 if and only if nodes I and J are connected. So the goal here, the name of the game, is basically that we want to infer the coupling matrix A and potentially the interaction functions G and F, but we'll assume here they are sort of given, right? And we're given measurements at the nodes at certain time. This comes typically in the form of trajectories. And so what we want to do is, given this data, we want to get some form of A hat, which is as close as possible to the matrix A, to the coupling matrix. And this would be the estimator. So this is the typical example. And here you have a picture that tries to do this. So, you know, there's a dynamical system. I'm not going to go into the details what this is about, but, you know, you can set this up and you can solve a sparse regression problem. And, you know, this is a super nice picture. You see, you start with something that looks like a Lorentz attractor here, and you infer the equations, and lo and behold, the inferred system, you know, gives basically the same thing. Of course, you know, this is a well-crafted example, and it's a nice paper, but this is not what I want to talk about. What I want to talk about now is basically, well, what if we do not know the network, right? And what if we cannot get the network, right? So in theory, these methods of inference, they work under certain assumptions. And one of the big assumptions is typically that you have sufficiently many samples, right? So if you have enough data, you can get a good estimator of the adjacency matrix. But what if we cannot learn the exact topology, meaning the exact A matrix, for example, because we don't have enough data, or, which is almost always true, if we only observe a subpart of the system, or if we don't get trajectories, so if we don't get trajectory data of all the nodes, but we only get snapshots in time. So you can think about maybe a gene expression experiment where you set up, you know, like an array of genes, and you let this experiment run, and at some point you measure the gene expression, but unfortunately that means very often that you destroy the system. So you can only do this once, and you only get this readout once, right? In the following, I'll concentrate on a scenario where basically data limitation or sampling limitations are the most important thing, and we only get snapshot data. But let's sort of step back a little. So I'm telling you now, you cannot get the A matrix. So why talk about this here? There is no network to be inferred. Everything's done, right? But here's the kicker, right? So very often we're actually not interested in the full network, but we're interested in some low dimensional representation thereof, or some interpretable features. And so basically we have a latent system, and this could be some sort of dynamical system. We measure the data. Now what you would typically do is you infer the network, and this is, however, not the end of the story. You then go on and you try to learn some, community structure, centrality measures, core-periphery. You analyze the network. And if this is indeed your goal, then there is still hope. And why is that? Because basically we're going from something that's lower dimensional, if we don't have enough samples, to something that's very high dimensional, to something that's low dimensional again. So if we could somehow, avoid this step in the middle, try to infer a point estimate, if you will, of the network, then maybe there's hope that we can do this here nonetheless, even if we just have very sparse data. All right, so I've visualized a few interesting network features before: core periphery structures, centrality measures, but there's others, right? So the spectral radius could be something that's also related to the network, which would be giving you some information about the dynamical stability of the system. Or if you think about things like the 6 degrees of separation. So what's the diameter of the network? Maybe that's something you could find out by looking at dynamics as well. But for this talk now, I'll choose a simple example, a very popular example, which is modular structure or community structure. And what I will basically try to do here, I will try to fit a stochastic block model, which is one form of modeling community structure in a graph. And basically the idea is now that given the data, instead of inferring A hat, which should be a proxy of A, what I'm trying to do here is to infer a model of A, which I assume has generated the adjacency matrix. And the trick here is that this model, right, is low dimensional, so it has a few parameters that we need to estimate. And this is what gives us the statistical power to do this. So now I've changed the game, right? Instead of trying to infer the matrix A, I'm trying to infer a probability distribution over the networks, right? And so here's this stochastic block model for those who haven't seen this before. So each node belongs to one of k classes, which we assume conveniently here to know. So we know there are k groups. Maybe there are 3 groups: students, postdocs, and professors, or something like this, right? And the link probability between those groups just depends on the group membership. So there is a coin associated to each pairing of groups, and you flip this coin, and if the coin lands heads, then there is a connection between you and the other person. So this is sort of like a schematic of this. So it's a fairly simple model. One can do this with more difficult models, but this is the one where we can prove things. So let's get going a bit faster now. So we have the following data generation model. It's a very simple LTI model, linear time invariant system, where the state is assumed to evolve according to a linear system. So the state x of t plus 1 depends on the state of the previous time. And this is mediated by a function of the adjacency matrix, which we assume here is known. What we're gonna get is I is indexing the number of samples, so we're going to get S samples of that kind. And the model proceeds as follows. First, we draw an adjacency matrix from our stochastic block model. We keep that fixed. Now we we draw another S samples X naught. Think about this as initial conditions. They're independent and identically distributed, SAP Gaussian. And now we basically, for each of these X naught, we take our stochastic block model, we run these dynamics up till time t, and we create the output sample from this. And we now have S output samples that we can collect in a matrix. And now the question is, can we get back the model that generated A? I hope that's clear. So here's the recap, right? We get S samples as sampled at a fixed time t. We know the number of groups k, and the model basically was, as I just described. Our goal is to get the partitions and the parameters back. Right. And here we go. Out of the hat comes the white rabbit. We can do it. And in particular, we can prove the following theorem. With high probability, we can recover the true partitions and parameters of this generative model, that is the stochastic block model, under some mild assumptions, which have to do with the model being, let's say, sufficiently inferable. So basically, if it's impossible to recover the network, even if you saw the full network, if it's impossible to recover the model, even if you saw the full network, which is known as the detectability limit, then you will have no hope of recovering it if you don't see the network. So this should be clear, but for more precise, discussion, I'll refer you to the paper that's out in Mathematics of Data Science. So for those of you who really, want to see a bit of math here, the more precise statement is that with probability at least 1 minus 5 over S minus epsilon, where epsilon is an arbitrary small parameter and S is the number of samples, we can basically show the following concentration result. And now I have to explain a little bit more here. So L is, let's say, the wishful thinking expected matrix. So L is like, I give you the full model in its expectation. And if I had that, I could just read out the parameters and the partitions. And what we can show is that we can approximate this thing with a sample covariance matrix sigma head. And basically, we can bound the distance between those two things. And now there are two parts of this bound. The first part has something that is basically an insurmountable error that has to do with the delta min, which is the minimal degree in this, the minimal expected degree of your block model. This has to do again with the detectability limit. So, the network needs to be sufficiently connected somehow. And we have another part that's not dependent, that's also dependent on M, but the time dependence of it is different, and only the second part depends on the number of samples. And if you look at this carefully, you see that the first term is actually growing linear with time. So this is going up. And now I have to tell you this M under the set of our assumptions is actually always bounded. So these terms here are smaller than 1. So M is smaller than 1, and actually you can show that this mu I, which is the eigenvalues of the expected matrix, is also smaller than ui. This is the sum of them are also smaller than 1. So B of t is actually contracting in time. So that means there is some sort of sweet spot, all right, that comes with the observation time. So you should think about it like this. If I observe my system too early in time, then my initial condition is basically, it hasn't evolved in time at all. It's all I see. Now the initial condition was random, so there's no information to be gained. If I wait too long, then this dynamical system will reach a stationary state. So we're looking at a linear system, and we've assumed that this linear system was stable. If you reach the steady state, there is no signal left. So that means that in between, there is this sweet spot where we can actually recover the partitions as good as if we saw the full network, and actually we can perfectly recover those partitions. we don't have to see the network at all. And the interesting thing is that this time trade-off, you know, basically, if you wait long enough, if you can wait long enough, then maybe 10 samples are as good as having, or even better than 500 samples early on. And I think that's a nice result. Sort of, it's an interesting trade-off there. So here are some future ideas for you to consider, and I should say some of them we started looking into as well. So please feel free to send me an email or look at my homepage or something like this, or on Santiago's homepage. So the questions are now, okay, let's look at the more general model of that form. What are the network features that we can actually learn here? I mean, I showed you something about stochastic block models. What about core periphery structures? What about centralities? Actually, for centralities, you should look at Santiago's work with Maze Roddenberry. They have something, and Hotay, another. So there is stuff, right? So this thing is moving. Other dynamical models. What about generalized linear models, where you put a nonlinearity here? Nonlinear models. David Gleich is going to talk about nonlinear models. Prior information. We could have other types of prior information than the model that we're assuming. So the Bayesians in the audience, here you go. Solve this with your favorite models and priors. And of course, there are connections to systems identification, causal learning, and so on that one could explore. So with that, I'll leave you with some references here that you can look at. And yeah, if there are any questions, please let me know.
Awesome. Thank you, Michael. Thanks a lot. So yeah, so remember that you can post your questions in the chat. So I see there are also some virtual claps over there. So thanks. Not to me. Thanks for joining in thanking Michael. So we have the first question here. So Francesco is asking, what are exactly the parameters in the SVM you're inferring?
So in the plot that I showed, what we're, of course that was bound to happen. Let's say new share here. In the plot that I showed, what we were inferring was the partition. So let's say the group assignment. I don't know why this is not like
we can see your screen, Michael.
Okay, interesting. It's not saying that I'm sharing, but okay, now it is. So where was the plot? So here I was inferring the groups, so the group assignments, and the overlap score is basically how good do you do. 1 is perfect, 0 is random, as good as random. And if you can also infer the parameters of the model, so you can infer the connection probabilities. So I see there's also another question by Peter Gringroth, joining us from Oxford, I presume. Why not have full coupled models when the dynamics evolves as a function of A, while A evolves stochastically as a function of the pairs of the end node states? I'm not 100% sure that I understand the question. Maybe we can quickly unmute.
Yeah,
Peter,
I mean, Peter, do you want to unmute yourself and maybe follow the discussion live?
Yeah, sure. Hi there, everybody. Really nice talk. I'm just thinking to myself that sometimes we want the adjacency matrix itself to evolve, maybe stochastically, as a function of the difference in states at the end nodes of edges. Edges could go pop, or new edges could appear if two nodes were sufficiently similar. So there's a kind of homophily driving, so that would evolve on the same time scale as the states of the nodes themselves, which are these ODEs, which are of course coupled up through the adjacency matrix. And it seems to me that we've often looked at dynamics on networks, and a really harder test is to look at dynamics where the networks and the nodal states are changing. That's all.
Yeah, so thanks. Yeah, that's a very interesting point. So basically, we could also try to look at linear time varying system where the A matrix, so now we have a system x dot of t, maybe A of t and x of t. I mean, we could also say it's just the adjacency matrix evolving, perhaps with some sort of Markov model on top of the stochastic block model that's there. Yeah, I think, I mean, that's definitely definitely an interesting direction to go to. So this is basically the first thing that we did in this direction. And yeah, I mean, if you want to talk more about this, feel free to send me an email. I would be interested to hear some more thoughts about this. Thanks.
Great. Thank you, Peter. So let's see, do we have any final question for Michael? Know that typing might take a little bit of time, so I'm just gonna wait here for a few secs. So maybe Michael, you can comment on so this function f of a, right? So Peter was just talking about changing a, but what could be done in the realm of keeping a fixed and changing f, having an f of t of a, right? F of t there, right? So what can be done there?
Yeah, I mean, of course, now there you go. I mean, you're sort of going through all sorts of options. Let's see what we had here. No, I mean, here actually L was, no, there was sample dependent, not time dependent. So the function can also change. So in particular, you can have uncertainty, let's say parametric uncertainty. You can have a class of functions, but maybe they are modulated by a few parameters. And yeah, there's work by a group in Texas on this from Rice University, and they have done something along those lines. And yeah, the last paper here that goes in this direction. I should say that we are not in, so basically we have parametric uncertainty on the function, but we're trying to infer the adjacency matrix exactly. But yeah, all sorts of combination are possible there. I think that's, yeah, it's just the start.
Awesome. Well, thank you, Michael, again for the presentation. So we hit 9:30 here. So we're gonna transition to our next speaker. But yeah, thanks again. I see